Hello, everyone. My name is Carver Johnson, and I will be representing on behalf of my team, Emerson Yahtzee and Robert McFadden, for Project Aeolus. I'll be sharing our capstone journey by highlighting some of the key experiences and findings we've had over the past 4 semesters. So, coinciding with JMU's commitment to encouraging environmental stewardship and bolstering professional development, in 2012, the Center for the Advancement of Sustainable Energy, or CASE, designed and built the small wind training and testing facility located on the east campus of JMU next to Rose Library. The facility kind of acts as a microcosm of the US Department of Energy's National Wind Technology Center in Boulder, Colorado, by providing research opportunities for students and small wind pioneers. The facility is characterized by a Berge XLS horizontal axis wind turbine connected to a small housing unit right below that contains various devices for data monitoring and power storage. Behind the facility is a plot of undeveloped land full of potential. So, CASE Executive Director Dr. Jonathan Miles and Wind for Schools Program Director Remy Pangel wanted to expand the infrastructure of the small wind training and testing facility. They've expressed high-level interest in the installation of a second turbine for the purpose of comparative analysis tests. And additionally, they've expressed the current infrastructure of the space kind of inhibits the JMU community accessing the space and does not possess adequate features conducive to a learning atmosphere. Therefore, Project Aeolus aims to install a vertical axis wind turbine as a counterpart to the current Berge XLS. And we will also be designing an outdoor courtyard area with workspaces and other fixtures to encourage user engagement. The goal is to provide unique value to the JMU community through the development of a new, captivating, and enjoyable renewable energy focused space on campus. So when first approaching this challenge, we decided that a solid foundation of technical knowledge regarding wind energy was crucial. Through our research, we learned the intricacies of wind turbine mechanisms and how they interplay with their environments. However, we also discovered two majorly adverse trends in the industry. Firstly, many turbine suppliers tend to overestimate the efficiency of their turbines. Many times we found that our own calculations using relevant equations resulted in different numbers, especially with regards to Betz' law, which states that no turbine can be more than 59.3% efficient. And some of these companies were reporting up to 80% efficiency for their turbines. So finding a dependable vendor proved somewhat difficult. Therefore, to ensure the sources were reliable, we needed to guarantee that the products were verified by the Small Wind Certification Council. Additionally, many users who buy wind turbines fail to investigate the meteorological context of their proposed installation site. When a turbine is rated for a specific power output, it is absolutely dependent on the environmental conditions. If a location does not have sufficient weather patterns, then the turbine, regardless of the certification, will not produce the prescribed amount of power. So historical data gathered from anemometers at 10 and 20 meters at the small wind training and testing facility were used to develop the probability distribution graph here. That will help determine the practicality of installing a second turbine in that location. This helps us compare the cut-in speeds of different turbines with the frequencies of the wind speeds found in the site. So if a turbine's cut-in speed, which is what's used to actually activate the spinning mechanism, would be around like 4 to 5 meters per second, then they weren't really considered a good candidate for further research because only about 6% of the annual wind speeds exist at that level at the small wind training testing. With help from Remy, we were able to determine estimates that helped us narrow down our choice of turbine. We wanted to yield as much power as possible while still adhering to the constraint of a low cut-in speed. And as seen in the top left figure, the DS3000 from Colite Industries far outweighed the competition, and it was also small wind certified. As depicted below, we then synthesized the power curve data from that turbine, which is not depicted, with the distribution model that we previously shown to obtain a theoretical representation of the turbine's power output. As you can see, the DS3000 has its kind of average high occurring in March and the average low occurring in July and August. And to understand the impact of this information, we kind of estimated a hypothetical square footage and a requirement of LEDs that would illuminate that. It was found that the DS3000 could generate about 205% of the lumens required in a high output season, like in March, and then about 41% of the lumens in the low season. But considering other factors like the second turbine in the facility that currently exists, energy storage units, and power grid connections, we're confident that the DS3000 is an optimal choice for the space. And one thing that I haven't mentioned yet is the cross-collaborative nature of our project. In addition to working with stakeholders from CASE, of whom are based out of the ISAT department, Project Aeolus has partnered with students from the JMU Architectural Design Department to help develop the conceptual design for the outdoor courtyard. Located approximately 1 mile away from NGO at point A, the ArcD students bring modeling and visual design expertise to the team. And seniors Caitlin Morgan and Richard Ong volunteered to help us by generating a full 3D model of the proposed space for demonstrative purposes. And just as an additional tidbit of information, the small wind training and testing facility exists approximately 0.27 miles away at point C from NGO. And so, in conclusion, recently we've generated a preliminary 2D site plan drawing using the Alpha 3D model given to us by Caitlin Morgan. And the model is still in early stages. But by the end of this semester, we still plan to pass our research on to Remy and John so that they could potentially continue the project, because they want to give our work to a new team of people and work on the things that we weren't able to cover during our time here at JMU. And we're proud to say that even if our project doesn't get brought to light, the small wind training and testing facility definitely accomplished its objective. Our work kind of stands as a testament to the objective of providing students with an opportunity to learn more about renewable energy practices. But best case scenario, if our work is continued with a new team going forward, then we think that JMU's community will be provided with something that's definitely unique and valuable. And we'd like to give special thanks to our advisors, Dr. Patterson, Dr. Enriquez, for their guidance in our efforts, and also thanking Dr. Jonathan Miles and Remy Pangle